Thank you. Hey guys, thank you. I'm ManishMaheshwari. Along with me, there's Quanlong Huang. He's sitting right here. We'll talk about Impala and how do we intend to make it a more intelligent query engine than what it is today. Okay. So just some Impala basics to begin with. Impala is a extremely large MPP database engine. It supports a variety of table formats. It supports a variety of deployments. It supports the Hive table format, the Iceberg table format. It supports Apache Hudi. In terms of file formats, we support Parquet, ORC, Avro, JSON, and other file formats. And it's supported on STFS, Ozone, S3, Kudu, and we also support HBase and other storage formats. It is an MPP engine. It basically uses a combination of Java for the front end and C++ as a backend, as most BI engines do today, for where the Java part is used for query compilation and the C++ part is used for query execution. We support enterprise grade security using Ranger, authorization, lineage, auditing, and also a variety of security mechanisms like Kerberos, LDAP, JWT, and we are adding support for OAuth and other authentication types. It's widely adopted. We are forked by other projects like Apache Doris and StarRocks. We have 1,400 customers, 97,000 nodes running Impala, and large clusters with more than 1,000, 1,200 nodes just running Impala. Okay. Oops. Slow.
There's some delay in this.
Okay. Okay. We talk about new features in Impala 4.4. The legacy Impala multi-threading model was very basic. You had to specify the number of threads, and the number of threads applied to all operators in the query. Obviously, this was user-specified number of threads, and it was not automatically being derived, which made it very inflexible for use. It could not be adjusted according to per operator basis. So some operators might require more threads, some operators might require less number of threads. It was not automatically determined. By setting empty DOP manually, that was not very preferred option for a lot of customers, for a lot of queries. What we have implemented is something called as workload aware autoscaling. And what workload aware autoscaling does is implements a cost-based model that determines that for every operator, what is the level of multi-threading required, and accordingly sets that multi-threading level for every operator, so that each operator can use a different number of threads and automatically improve query performance. What it also does is it basically allows you to then decide what query pool you need to submit your query to. So according to workload aware autoscaling, the planner takes a query in consideration, and then it replans the queries to determine whether the query, according to memory and CPU estimation, should either run on a small pool or a medium pool or a large pool. These different pools are different executor groups. The small pool might have 2-4 executors. The medium pool might have 10-15 executors. The large pool might have 20 to 30 executors. Accordingly, each query is replanned and sent to a right executor group, so that each query can be scheduled on a executor group that has the required memory and CPU to meet the requirements for that query. Each of the executor groups also automatically can scale up and scale down, and according to the workload that is submitted to those executor groups, which then allows you to have one environment to handle a lot of mixed workloads. Many times we have seen customers have to deploy multiple environments for different queries to be run. Multiple environments then allow them to have a good control on small queries, medium queries, and large queries. By having workload aware autoscaling, what we are able to do is in a single environment using multiple executor groups, you are able to handle both small and large queries, and each one of the executor groups can scale up and down independently, basically allowing better throughput for a complex workload to run on Impala. The way this works is in cloud native interfaces where you have deployed Impala on Kubernetes. You have SQL clients come in, and for each of the SQL clients, for each of the queries that are submitted to the SQL client, the coordinator will determine what executor group should the query run on. You have multiple, we are showing two executor groups over here, and each one of them can automatically scale up and down according to workload. Using VAS, the Impala coordinator would plan and determine the CPU and memory requirement for that query, and accordingly it will assign that query a group set 1 or a group set 2 where the query would run. According to the number of concurrent queries, the executor group sets can also independently scale up and scale down, so that if you have a combination of only large queries, you'll have a large scaling on this executor group. If you have a combination of only small queries, you'll have a auto scaling on this scale of groups. Each executor group can scale up automatically up and down according to a workload. We also enable that we have consistent hashing, and what that enables is within each executor group, we are able to utilize the remote file cache accordingly, so that you don't miss the benefit of cache data and metadata. Okay. What are the benefits of VAS? Basically, instead of running multiple clusters within a single cluster, having multiple executor groups allows you to run differentiated workloads in a single environment. This also allows you to have a lot of easier programming on the client side, where the clients do not need to configure multiple JDBC endpoints to submit queries. So whether it's JDBC clients, whether it is CLI clients, all of them can submit queries to a single endpoint, and within that single endpoint, by having multiple executor groups, you are able to handle all kinds of workloads without having to create separate clusters. We have seen some deployments from other SQL tools, and what they do is they implement something called as a query routing. And what query routing does is you have a query router in front of multiple clusters, and then it routes queries to clusters depending on their availability and their size. Instead of doing it across multiple clusters, we are doing it within the cluster itself, so that within a cluster, according to the size of the workload, you can route queries to different executor groups. It gives a single JDBC endpoint. Eventually what we'll do is we'll also have the ability to auto size the executor groups, which means that we would be able to determine whether the small executor group needs to be 4 nodes, 6 nodes, 8 nodes, the large needs to be 20 nodes, 40 nodes, 60 nodes. So according to your workload, your executor groups can also get eventually automatically sized. With this, we have tested with TPCDS queries. So we selected a subset of 36 queries to represent small, medium, and large queries. And we have seen overall a 17% reduction in the overall compute hours. So without VAS, if you run the same set of queries, it takes more time, basically more compute hours to finish the workload. With VAS, you see a reduction of 17% of compute resources required to finish the same workload. We also see a 14 to 20% improvement in the throughput of small and medium queries. Without VAS, what we used to see is small and medium queries are waiting for the large queries to finish. With VAS, what we see is your small and medium queries are executed on the smaller executor group that allows small queries to start and finish faster, while larger queries continue to run on the larger executor groups. The next improvement that we are bringing on to Impala is query log tables. We have seen query log tables in a lot of RDBMS like Oracle, MySQL, Postgres, and others, right? What we have seen over the last 8-10 years is when you have a huge Impala workload, it's very difficult to manage that workload without a good workload management solution. You want to understand user behavior, you want to understand what tables are frequently queried, you want to understand what columns are frequently queried, you want to understand how much metadata operations is happening on the cluster, you want to understand what queries are running slow, and all of that is very difficult when you have like 5 million queries running every day. Right? A lot of customers have implemented custom code which used to parse Impala profiles, and by parsing Impala profiles they extract the required metrics and then write it back into HDFS or write it to a MySQL database or some database to then understand what workloads are running on Impala. To improve this, Impala now supports two sets of tables: the assist.impala query log for historical queries stored in the iceberg table format, and the assist.impala query live for live running queries that we extract from all of the Impala coordinators. What this basically allows you to do is we store every query that is run on Impala into the log table on a periodic basis, and we allow every live query to be accessible via the Impala query live table. Eventually what this will also allow to do is improve the behavior to run and manage live queries by allowing kill queries and other features that we are planning to add. So the first table, the query log table, right? The benefits of something like query log table, it will capture all of the tables that are queried, all of the columns that are accessed by the user that is running the query, what kind of query operation is it select, update, delete, drop. It will also capture information like refresh table commands, invalidate table commands. And by doing all of that, you are able to identify what are the tables that are most frequently accessed for maintenance operation, for iceberg table compactions. You are able to understand what users are running, how many queries on what tables, and how large is their workload. You are able to understand what columns are being used for joins, for aggregates, for filters, so that you can capture statistics on only those columns rather than capturing statistics on all of the table columns. You can capture query plans for MV recommenders. So we plan to capture the query plan and then feed it into a recommendation engine so that the MV recommendation engine can recommend what materialized views should be built on those tables. We can understand which users are running refresh table commands, which users are running invalidate metadata commands, and see at what frequency they are running. We can understand server level parameters like concurrent queries running, number of queries processed every hour, analyze workloads to understand whether your workload is mostly select, is it update, is it delete, or what kind of workloads a user is running. For live tables, you can track all queries running concurrently across multiple coordinators. In the past, every coordinator used to have a UI, and from the coordinator UI, you could look at currently running queries. Now with Impala, if you have multiple coordinators, and for most large clusters you have multiple coordinators, you have to go to each coordinator to understand what queries are currently running. With sys.query, with the live query table, Impala itself reaches out to all the coordinators to understand what are the live queries running, and then we are adding the ability to also kill a query. So if you want to kill a query that is running for more than 10 minutes, you can run a SQL command to kill queries that are running more than 10 minutes. If you want to kill queries that are run by a specific user, you can run a SQL command to kill queries run by a specific user. You can do that at a query level, you can do that at a session level according to what you prefer. We can also understand behavior from users. So we have some users that set sync DDL, we have some users that set very high memory limits, and what we are able to do with a live query log table is understand what user is setting sync DDL to true, or what user is setting high memory limits or running on a single node, and be able to kill those queries because of the bad user behavior. What are we capturing? We are capturing which user is running the connection, what coordinator it is connecting to, the status of the query, what type of query it is, whether it's a select, DML or DDL. We are capturing what time it started, from what IP address did it originate, what resource pool it is running on. We are also capturing admission results of that query, whether it's admitted or waiting to be admitted. If they are successfully run, then how many rows were fetched, all the event timers for all of the query DAG status. So once a query is submitted, it gets admitted, it has a single node plan, a distributed plan, the plan gets submitted to the executors. If it's waiting for catalog metadata, then how much time did it wait for catalog metadata. So all of those metrics we are going to capture as a part of the query log table. Finally, we will also capture the memory estimates of that query. So what was the estimated memory for that query, and what is the actual memory of that query, and what tables were queried, what columns were joined on, what columns were aggregated on, what columns were used for predicate filtering, what were the order by columns and what were selected columns. This then allows you to understand column usage of your data, then allows you to understand what columns you need to capture stats on, what tables are queried, what tables you need to capture stats on. Capturing the SQL and the plan will also further allow us to work on MV recommenders so that we can recommend what MVs should be created. Just a sample query. So here we are trying to find out that by the database name and the username, how many queries are being run, and just report it out. Right. Some future work that we are working on. So we want the compute stats command to be improved, for the compute stats command to take in information from the query log table so that we can automate the work of compute stats. Right now, we recommend stats to be collected on a weekend, and we don't recommend on what column should the stats be collected. So with this, we'll improve the compute stats command to automatically read the tables and the columns from the query log table and automate stats collection. We also need to plan to improve on query plans so that we can implement something that in the industry it is called a history-based optimizer. What a history-based optimizer does is basically it looks at your earlier query plans and then tries to improve your current query plan, learning from the history. Basically, for a similar query in the history, if you had a bad join order, or if you overestimated memory, or you made any other mistakes that resulted in either a bad join or a skew or anything of that sort, your newer queries can learn from the mistakes of the earlier queries and then improve the query plans. We have seen other SQL engines like Spark improve significantly using a history-based optimizer, especially in terms of resource optimization. So even if your plan is perhaps accurate enough, your resource estimates can be widely off than what the user estimated the memory that would be required than what the actual memory estimates would be. And using a history-based optimizer, you can improve resource utilization. You can also feed it into materialized views for MV recommendations. We also added JDBC Federation in Impala. So our recent release for Impala added support for a remote Impala cluster. a remote MySQL database, and a remote Postgres database. So all three are the databases that we currently support for JDBC Federation. It is basically implemented at the table level and not at a database level. So you do need to define JDBC tables one at a time. But even with that limitation, we see a lot of customers interested in federating against MySQL or against Postgres databases. We also see a lot of customers want to federate against other Impala clusters. So if you are running Impala in the cloud, or you have multiple business units and all of them are running Impala, you want to connect from one Impala cluster to the other Impala cluster, you can do that using JDBC Federation. We hotload the drivers from the object store at the runtime, so you don't need to provide the drivers beforehand. With the calcite parser, we further plan to add support for other JDBC SQL dialects. So right now it's MySQL, Postgres, and Impala, but in the future we plan to add support for other JDBC databases like Oracle, SQL Server, DB2, and others. Data is read on the coordinators and then handed over to executors for other query operators. Just a sample syntax as to how we are defining a Postgres connection. So basically you create an external table stored by JDBC with the table properties, and once you have defined it, you can just use it like any other Impala table. Similar for Impala connections. For other Impala cluster, you say I have a remote table, external table called as student JDBC stored by JDBC, and you set the database type to Impala. Push down operators for more remote databases, and also support distributed plans involving multiple JDBC tables, which we don't support yet. We frequently saw a lot of machine learning applications use Impala to fetch data from their big data environments. A lot of time when these machine learning applications used to fetch data from Impala, they used to be a performance penalty when you're fetching 10, 20, 30 million rows from Impala, right? So for fetching 10,000, 20,000 rows, it's fine. But when you're fetching millions of rows, there used to be a performance slowness because you are doing a single threaded fetch. What we added in the latest Impala driver is we added support for multi-threaded fetch. So at the time of fetching data from the database, you can use multiple threads, and by using multiple threads, you are able to fetch data faster using the same connection. So we added support for multi-threaded fetch, and the client application can fetch data much faster. We also added support for improving Impala timers, so that any time that you are fetching 100 million rows, you are able to identify where the fetch bottleneck is. So whether it's with row materialization, whether it is with sending the results back to a client, or whether it is with any other operator while doing the fetch operation. Overall, we have seen at least 3 to 5x improvement in fetch performance, leading to a point that we are able to almost maximize Impala row generation capacity to the fetch capacity. So the rows can be fetched by the client at the same rate as which Impala can generate those rows on the server side. I'll hand over to Quanlong to talk about future roadmap for Impala. Thank you.
Okay, thanks, Manish. So I will use Chinese in the following slides. 感谢大家做到最后。后面我就用中文讲。OK。我们在 Impala 4.3的时候引入了一个叫 Query Timeline 的这么一个功能，就是把一个查询，它有很多个 Plan Fragment， 然后每个 Plan Fragment 它是怎么进展的。什么时段是做 prepare， 什么时候做 open， 什么时候做 get next， 还有最后到 close。这个阶段我们把它画成了一个甘特图，然后在上面这个小图是 4.3 的时候就有了。 然后为了更确切的知道当时那个场景使用了多少线程，就是这些 CPU、内存、网络、磁盘的开销，我们在4.4又引入了下面的这些图，然后把这些 metrics 都可视化起来了，这样你就能更直观的看到我当时那个 plan fragment 很 busy， 它处于一个比如 GetNext 的状态，那个状态下它这些 CPU、网络、磁盘啊等等的这些资源是什么状态？对，我刚才开始讲的就是 observability 这方面的我们的一些提升，然后这块也是在这个可观测性上的一个提升。就以前 Impala 它的这个 DDL、DML 它的执行啊，虽然在这个 coordinator 的 queries 那块有一个记录，但是那个每个 DDL、DML 它的具体执行是在 catalog server 里面去执行的，然后这个进展其实在 coordinator 那一侧是不知道的，在 coordinator 的网页里，你只会看到一个 query 处于created 的状态或者处于 running 的状态，然后具体它进展到什么样了是不知道的。所以在4.4呢，我们在 catalog server 的网页上也加了一个 operations 的这么一个网页，然后这个页面就会展示所有 ongoing 的或者 finish 的这些 catalog operations 啊，比如说你有一个 create table as select 的语句。那这个语句其实它有2个 DDL， 一个是这个 create table 的部分，另外一个是insert 的这一部分。那在 coordinator 内侧你就只看到一行记录，然后在 catalog server 这边你就能看到这个 create 做完了没有 ，insert 做完了没有，用这个页面。然后还有一个可观测性的提升就是我们在 Impala 的 query profile 里加了 DDL、DML 的执行流程的这个 timeline。就以前的话，你在这个 query profile 里只能看到说一个 DDL、DML 它在 catalog server 里花了多长时间，可能10几秒、几分钟，甚至1个小时都有可能。那具体这个时间是花在哪了？那一般我们是得去查 catalog server 的日志，然后在日志里根据那个线程 ID 啊去绑定啊，然后去分析它为什么卡了那么长时间。然后现在我们把这个 query timeline 也加到这个 profile 里面去了。比如说一个 compute stats 的一个语句，那最后在这个 profile 里就会显示成右边的这么一个 timeline。以前的版本你只能知道第一行的信息，就这 calculate operation 花了6秒的时间。那这6秒具体是花在哪？比如说是在跟 name node 的交互，还是跟 high meta store 的交互，还是说它自己的一些数据结构的锁等等。那我们是要查日志才知道的。那现在在 query profile 里就直接把这些信息都展示出来了。那在右边高亮的部分就是这个主要耗时的时间，那你就能看到这个主要时间是花在 high meta store 的 auto partitions 的这个操作，然后你就可以针对性的，比如说考虑一下是否要减少分区数啊，或者是减少 compute states 的那个列的数目等等来优化，这样就很直观。然后以上是 observability 相关的一些优化。然后我们在 Iceberg 方面其实也加了很多新功能，我们一直投入的就是 Iceberg 的这个表格式。然后4.3之前其实也做了很多工作了，基本的功能都支持了。4.4的话，我们就更完善了这些工具集以及一些其他的功能，比如说我们支持 Iceberg VR 的 update 语句，我们支持 job partition 语句，然后支持用 optimize 语句做 compaction， 还有支持读取 equality delete 的 VR 的表。然后也支持用 SQL 语句，用 select 语句去查 Iceberg 的元数据，然后也支持建表的时候指定组件啊等等，然后Iceberg VR 表的读性呢也有很大的提升。然后我们今天其实有其他3个 Impala Iceberg 相关的 talk， 所以这里就不展开了，大家可能已经听过他们的一些分享了。下一个是一些其他方面的改进，比如说这里只列了一些值得一提的改进，比如说 runtime filter 的聚合一直是这个 coordinator 比较耗时的一个事情，就runtime filter， 特别是你做 partition join 的时候，你的所有的这些 runtime filter 生成的都是 partial 的 runtime filter， 最终要在 coordinator 聚合成一个 global 的 runtime filter， 然后再下发回所有 executor 里面去。那这个在大集群上对 coordinator 的压力是特别大的，比如你集群数达到700、800个节点的时候，这所有节点都要把它 partial 的 runtime filter 发到 coordinator 来做聚合。 那对 coordinator 的压力就特别大，然后你查询并发越高的话，对压力越大。所以我们在4.4把这个功能给下放到了部分 executor 里面去做。就我们先选定一批 executor 做这个预聚合，大家先到这些 executor 里做好预聚合，然后最终再发到 coordinator 来做一个最终的聚合，然后用这个 query option 来指定说我拿多少个 executor 来做这个预聚合，这就是分担了一下 coordinator 的这个压力。然后第二项是我们开始支持 JSON 格式的表，然后也做了很多增强的功能，比如提升 const 的性能，或者支持这个读取压缩的 JSON 文件等等，这个是网易的同学贡献的，代码也写的特别优秀。然后第三个是 state store 的 HA，我们在之前的版本已经支持了 catalog 的 HA 了，所以 Impala 在做完 state store HA 之后，就相当于整个所有的 HA 都做完了。值得一提的是 coordinator， 就 Impala 本身的 coordinator 本身是已经支持 HA 了，本来就可以有多个，所以做完 catalog 跟 state store 之后，也就所有的 HA 都支持。然后下一项就是支持打包成 RPM 或者 deb 的这些包。Impala 以前的部署是比较痛苦的，如果你没有买 CDH 的产品的话，要自己没有 CM 去部署 Impala。可能你要自己打包，自己选择哪些文件拿出来打包，自己去分发、去部署等等的。然后我们在这个版本就加了 RPM 的支持，然后大家也更方便的可以去部署 Impala。然后下一个值得一提的就是 Small Stream 的 Optimization， 就是Impala 是一个行式的布局的内存结构，因为它基于 CodeGen 的那个思路去做。然后行式布局的这个 tuple 里面，对于长字符串其实是有一个指针指到某个地方，然后还有一个字符串的长度这么一个结构体的。但这个结构体对于一些短字符串来说，可能你这个短字符串直接就可以放在这个 tuple 里面的这个指针跟长度这占的这个空间里面了。所以我们做了短字符串的这个优化，就直接在 tuple 里面放这些短字符串，这样的话就能很大程度的节省这个内存的开销。然后下一个就是 Event Processor， 我们开始能支持自动的跳过一些错误。以前的 Event Processor 特别脆弱，就是一旦遇到一些 Event 处理失败的话，它就会卡住，然后需要你手动的去执行 Invalidate Metadata， 然后这对整个集群的这个 impact 也是比较大的。所以我们开始尽可能的去自动的去 Invalidate 这个 table， 然后跳过这个错误。然后最后就是我们改善了 CodeGen Caching 的实现，这样使得我们可以更好的预估它的内存。然后还有一些正在进展中的项目，就很多项目它比较大，不是在一个版本或者1-2个版本能做完的，所以下面列的这些是已经开始的项目，也是想介绍给大家。如果大家有兴趣的话，也可以参与这些的开发。一个就是 Calsite 的集成。我们希望在 Impala 的Planner 里集成 Calsite。Impala 本身是有一个 Planner 的，那个 Planner 在生成这个执行计划的时候使用的是那种 left deep 的那种 join tree 的方式，生成不了 bushy join 的那种 plan。那引入 Calsite 的话，这方面的这个plan 会生成的更好一些。当然其实 Impala 这个 Planner 已经存在很长时间，可能11-12年了。它一直能存在，而且能 work 的这么好的一个原因就是 Impala 的 runtime filter 做的特别好。然后 runtime filter 就相当于其实做 runtime 的 bushy join 了，所以也不太需要 Calsite 的集成。所以另外一个我们需要 Calsite 集成的，其实是我们需要 Calsite 的集成进来之后，可以更好的支持 Hive 的这些物化视图。所以这是最主要的一个原因吧。然后我们现在这个集成做了一个初步的版本了，基本的一些 select 查询都能支持了。当然未必是一个最优的状态，所以大家对 Calsite 比较了解的话，也可以参与这个工作。还有这个中间结果的缓存，这个其实就是说很多比如 group by 的结果，或者是一些高基数的这个选择的结果，可以缓存下来，然后在不同的查询之间共享。然后这个工作我们是加入一个 tuple cache node， 然后这个节点如果有 cache 的话，就使用这个中间结果缓存；没有 cache 的话，就会把中间结果写到 cache 里，然后供以后的查询用。然后这个缓存是缓存在磁盘里，可以供当前这个 worker 的所有其他查询去使用。然后这个我们也是处于一个 刚做完原型的阶段，就是现在只是缓存了 scan 之后的这个中间结果。当然 Impala 的 scan 跟其他系统的 scan 还不太一样，就 Impala 的 scan 不光是做读取，它还会做 projection， 还有做 filter。所以如果你的这个选择的列比较少，然后你这个 filter 过滤的数据又特别多的话，其实这个 scan 的结果也不会特别多，然后缓存下来也利用率也比较高。当然我们希望继续把其他 operator 的这些 cache 都给支持一下，包括那些group by 的结果啊，或者是 join 的结果啊等等。然后还有其他的工作，比如我们集成 kill side 之后，可以支持这个公共表达式的删除啊。比如说你一个 view 在一个大查询里用了很多次的话，它那个查询结果是否可以复用啊？然后我们支持在 REST catalog 支持 REST catalog 上的 iceberg 表，然后也提升一下扣件 caching， 还有这个异步扣件的这个集成，还有在 catalog stability 方面，我们想提升一下，主要就是想提升一下 catalog server 的内存使用，因为现在有的机器在 production 上可能达到了300G 的内存，然后这个内存开销还是比较大的，我们希望做一些更细粒度的这个 metadata 缓存等等的。然后刚才 Manish 也讲了这个 query history 来提升这个 query plan 这个事情，这个也是我们希望这个引擎能更智能的一个方向。因为有了 query history 之后，你很多之前那些错误的预估，不管是极度的高估还是极度的低估，你就可以用 query history 来调整一下。然后或者说你可以先跑一些查询，教会这个引擎说我这2个 group by 列其实是非常相关的，你不要把它当成独立的2列。或者你可以跑一个 select 查询加一个 filter， 然后让这个查询看一看这个 filter 的这个条件是不是选择性特别高，就是不是它能过滤大部分数据等等。这一类的信息其实可以通过这个已经跑过的查询来获得，然后你再给它一个更复杂的查询的话，我们希望它能用上这些简单的信息来避免产生特别差的查询计划。OK， 后面就是联系方式，主要就是我们的邮件列表，然后如果用 Impala 有问题的话，可以在这个issue链接里提。然后我们有 Twitter、Slack， 还有这个微信公众号，大家可以加这个公众号，然后有一个 Impala 的国内的微信群，使用 Impala 有任何问题都可以在里面讨论。好，就是这样，谢谢大家。